how do you calculate these probabilities by hand, so to speak, with a table? So here's a problem from the Statistics Using Technology textbook, and we see that the mean starting salary for nurses is 67,964, and the standard deviation is approximately that. They're telling us. Then they're telling us to assume the starting salary is normally distributed. Usually salaries aren't, but that's okay. So state the random variable. So what's the random variable? Well, because we're talking about single nurses here, I think it's just the nursing salary. The salary a single nurse would make. If we started doing it with samples, like in the latter part of chapter 6, well, then we'd have to worry. It's a sampling distribution. We'd be talking about the mean salary. So since we're talking about a single nurse, that's what we have now. So that's a random variable. And then because this is a normal distribution, I set up a normal curve table. I use the applet to do this so you could read it. It's not instead of having to deal with my writing. And this is plus or minus 1 standard deviation. Remember, 68% of the distribution of salaries fall within that range. That's plus or minus 2 standard deviations. That's 95% of the salaries will fall within that range. And then, of course, this last one way out here is plus or minus 3 standard deviations, and almost all, or 99.7% of the salaries will fall within that range. So there's a chance, there's a small chance that somebody will learn more than that or less than that to start with. So that's the setup. Now, we aren't going to be able to use these numbers because none of the numbers are these nice, neat, empirical real numbers, but it just gives us an idea. So for part B, they want us to find the probability that a starting nurse will make more than $80,000. So I took that same sketch. What I want you folks to do, even if you're using technology, is make a quick little sketch, put the mean in the middle, mark 80,000, and then shade above it. And that'll help you decide what to do with the normal CDF and all that. Now, to do this by hand with z-scores in the table, I have to calculate a z-score. I have to standardize this value. So remember, z-score is the number we're interested in minus the mean divided by the standard deviation. So for this problem, the z-score is going to be 80,000 minus 67,694 divided by 10,333. And the process is subtract those, divide by, and get that answer, then divide by that. The mistake that somebody makes usually when they're doing this work is they'll take the 80,000 figure, subtract the $67,000 figure, then hit divide without hitting equals, and then they'll divide by the. I didn't write down all the numbers just so you see. And this is if you just do it this way, that's going to follow order of operations, which is going to do this division and then subtract it from 80. I mean, if you want to do it all in one string, throw parentheses around the things you're subtracting. Okay. So when I did this, I got 1.19 for the z-score. And the thing about these normal curve tables, and they're all like this, they always tell us the area to the left. So when I go to look this number up, that's the area to the left. And if you remember, if you look back to the sketch I made earlier, I want to know more than 80,000, or in this case, more than 1.1, a z-score 1.19. Okay, so I'm going to have to take this table answer and subtract it from 1. So let's find this. So the way you read these tables, it uses the first 2 decimal places, well, the whole number part, and the first decimal place, you use the column. So I'm going to come down till I see 1.1, and then 0.9 is this column. I'm going to come way over here, and I'm going to have to, my eyes are jumping this morning. I'm going to highlight that. And if I come down, and I look at that intersection, I'm seeing that number there. Yes, the 1.1, the 0.09. So that's the probability to the left. That's that black area. To get the white area, we have to do 1 minus that number. So 1 minus 0.8830. So calculating this on my calculator, subtracting those, I got that for an answer. So that's that red area. And then I decided to do normal CDF just to see. Notice I get the same value. So looks like we did it right. So for this part, same distribution. And we're looking for what's the probability that a nurse will make less than $60,000. So here's this about where 60 falls, in between 1 and 2 standard deviations below the mean. And that makes sense because that's less than the mean. So we got to do the z-score. So z, let's see, the number we're interested in is 60,000 minus the mean divided by the standard deviation. And remember, you're going to do that, type those numbers in, subtract them, and divide that by that answer. Remember to hit equals first. So when I did this earlier, I came up with a z-score negative 0.74. Makes sense that it's negative because it's below the mean. So I'm going to go to my z-score table. And let's see, I'm going to slide it over so I can see the 0.04 column. And let's see, negative. So negative 0.7. And then the 4 column is the 5th one over. Here, let me put it right over the side of the screen. So negative 0.74 is that area. It's that area. So the table is telling us that the probability is 0.2296. Now, because when I made my sketch, I've got that $67,000 figure there. I've got my $60,000 figure there, and I want the area to the left. And these tables always give us the area to the left. So that is the exact answer. We don't have to do any subtraction to get it. And we could check and do normal CDF, but I know I'm right. So for now, we're looking for an area between two salaries. And that's this area. So notice I made a sketch. It really helps to do this. So what we're going to do, here's the process. We're going to find a z-score for the $55,000 figure, and that'll give it, and then look up the probability, and that'll give us that area. Then I'm going to find the z-score for the $72,000 figure. Look up that area on the table, and notice the overlap. So then I'm going to subtract the $55,000 probability from the $72,000 probability, and that'll be the probability in between. So to set up these two z-scores for the $55,000 one, I'm going to do 55,000 minus 67,694 divided by 10,333, and I have that answer on the next page, in the next slide. And then this one is going to be, what, 72,000 minus 67,694 divided by 10,333, and I get that answer. So remember, you're going to do the subtraction, get the answer, then divide. Then you can do the subtraction, get the answer, then divide. One thing to keep in mind when you're working with the table is only accurate to 2 decimal places, so round your answer to 2 decimal places. So here's the z-score for the $55,000 figure, and the reason I know it's the $55,000 z-score because that's below the mean and it's negative. So if I go to my table, let's see, I think I need to, I hope I left both tables here. I didn't. Well, let's look up the 0.42 right now. Let's see, 0.42. 0.42 is that probability right there. And that makes sense that it's more than 0.5. So that probability is 0.52. I better circle it. 0.42. So 0.6628. So here's the negative z-score table, and I'm looking for negative 1.23. So let's see if we can come back and find negative 1.23. I think that's right. 0.03, negative 1.2. So 0.1093. So now this is the area. Let's see, I don't know if I can drag everything without moving it all. So this area is that one, with a 55,000. And here's the 72,000, and that's the 0.6628. So I need to subtract those. So I'll do that off screen on my calculator. So that's what the calculator is telling me the probability in between those two amounts are. So about 55% of the nurses earn between 50,000 and 72,000, and normal CDF gave me approximately the same number. The reason this is different is because of all the rounding I had to do in order to use this table. Which is more accurate? I don't know. At the nearest thousand, it's certainly the same. So for this question, we almost don't have to do any calculation. In fact, we don't have to do any calculation. We can answer this question without it. Remember back when we were looking at distributions, and we said if the shape of the distribution is symmetric, we're going to use this mean and the standard deviation, and the rule for an unusual result was if we were more than 2 standard deviations away from the mean. And notice that $50,000 is, let's see, that's 1 standard deviation below the mean, that's 2 standard deviations below the mean. Since the 50,000 isn't more than 2 standard deviations below the mean, we wouldn't think the nurse was underpaid. I mean, it's just a small amount, but we wouldn't think it's underpaid. Now, if we want to look from a percentage point of view, let's see what happens there. We got to do a z-score, of course. So z, because we haven't done this calculation yet. So 50,000 minus 67,694 divided by 10,333. And if you do that, you get a z-score negative 1.71. We knew it was below the mean, but not 2 standard deviations below the mean. So I go to my table, and I look up negative 1.7, and they come over the 1 column. I'm seeing a probability of 0.0436. So that is less than 5%. So if we wanted to go from the percentage route, we could say, yeah, there's some evidence that she's underpaid. It's because this is symmetric distribution, I almost don't think we would, but I don't honestly know what the back of the book says. We'll see shortly. We'll see in chapter 7 a way to come up with a rule of thumb to make that decision. Okay, last part. We're looking for, we don't know the salary that cuts off the well, actually, at the 30th percentile, if 30% of the nurses earn more than that, that's like that. The reason I chose to draw it there is I know, but from the empirical rule, that 16% of nurses earn more than 1 standard deviation above the mean because of the middle 68, right? If it's the middle 68, well, let's see here. If I go 1 standard deviation either side of the mean with a 57, 361, and the 78,027, if 68% of the nurses earn in between those amounts, that'll be 16% earn more and 16% earn less because they have to add to 100. So we know that it's somewhere, and we know the mean is the 50%, the 50th percentile, so it's somewhere in between. It's somewhere in between 0 and 1 standard deviation above. And so we'd need the task is to figure that out. What is it? So we're going to go to our handy table. Actually, before we go to the table, remember that table always tells us areas to the left. So if I'm looking for the top 30%, I'm going to look up in my table 0.70. So the difference with this is I'm going inside my table, and I want to find as close as I can get to the 0.7. And this is 15 10,000ths below. This is 19 thousandths above. So technically this is closer. However, since we want to have the top 30%, and some books are picky about this, this would allow more than 30% of the nurses to earn that. And granted, it's not much. I mean, we're talking about 1/100th of a z-score, so of a standard deviation. But to do, technically we should probably use this one because this will make it a little high, but at least we won't have more than 30%. So the z-score I'm looking for is 0.53. So then I use the z-score formula, and I wrote the z-score equals the number I don't know minus the mean divided by the standard deviation. And then the algebra we have to do to solve this is, just remember, this is like a proportion, so I can do the cross products. You didn't know you were going to have to do algebra here, huh? Equals x minus 67,694. So we're going to multiply those two answers, those two numbers, and then we're going to add the 67,694, and that'll be the number that cuts off that top 30%. So I did that on my calculator, and I came up with $73,170 about, and then I chose to use that inverse normal, and that gave me that number. So quite a bit lower. So what was the difference? Well, remember how I had to make that decision about where I was going to round? So that explains the difference. The calculator is able to produce a value for exactly 0.3 or 0.7 to the left, and we had to do the estimation. So that's how you do this with z-scores and the table. That's how we did it, quite, right up until probably the last 10 years in a statistics course. This is how you folks would have done it.